Hello again, everybody, and welcome back to the Geo-Institute Summer of Live. Yes, we have many amazing live events for you this summer, and we'll talk a little bit more about those in a bit. My name is Brad Keeler. I'm the director of the Geo-Institute, and once again, welcome to our second of three live events for you this summer. And we'll talk a little bit more about those in a bit. 24-25 lecturer Richard Bathurst. We've got another great presentation for you today. We'll be getting to that momentarily. In the meantime, if you don't know anything about the Geo-Institute, after you watch this lecture today, let your fingers walk you over to geoinstitute.org, and there you will find out a great many things about our august institution, such as we are a technical institute with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and I would encourage you actually to preemptively do this because I'm telling you, you're going to like what you see today. You should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. One final reminder. You can obtain your very own Ralph Peck bobblehead. This could be in your home. The way to do this is when you go to geoinstitute.org, there is a link in the top right-hand region of the page that says something like Student Participation Fund. If you click on that and follow the prompts and make a donation to student programs of $96 or more, you will receive your very own Ralph Peck bobblehead. We ship it to you if you live in the US and Canada. If you're somewhere else, you'll have to pick it up at one of our events. But we're very friendly, and we will bring it for you, and it will have your name on the box. We promise. One final thing before we get to our big presentation today. We are very fortunate and very grateful to have an amazing sponsor for the Cross USA Lecture Series for the, I believe, fourth year in a row. It is GeoPeer, and we have a brief message to share with you from them today. We're only going to play that video once for them. That's part of the agreement. Now to introduce Richard as the chair of the Geo-Institute Local Involvement Committee, who can maybe tell you a few things about the Cross USA Lecture Series, and then tell you what Richard's going to tell you today. He is the newly minted Dr. Jay McKelvey. Jay, thank you for doing this. Take it away.
Thank you, Brad. Hi, I'm Jay McKelvey. Yes, I'm the chair of the Local Involvement Committee, and part of that committee, we actually select who are the recipients of the cross-country lectures. So we just picked 3 for the next year, and we have 2 GSOs. I don't have the list in front of me, and that list would be given out on Friday, but it's a great honor to be involved with this. And a few years back, we were looking for some possible lecturers, and I reached out to Richard, and he was all about it. So it actually worked out real good. So let me not take up too much time. Richard is a true geo legend or geo stud. Professor Emeritus at the Royal Military College of Canada, and he also has a cross appointment at Queen's. I think he's authored over 230 papers and probably has been involved with so many other scholarly contributions associated with geosynthetics and specifically with reinforced earth. He's a 2021 recipient of the Middlebrooks Award. Basically, he wrote a paper that was considered the best of. He's the editor-in-chief of the Geosynthetics International and also International Journal of Geomechanics. And he's also involved with several other technical journals. He was recently elected as Fellow of the Royal Society of Canada, which is probably the top honor in Canada. Do I have to kiss your ring for that? So you could read Richard's accolades for about another hour and a half. So I'm just going to skip all that. And again, I'm very proud to introduce Dr. Richard Bathurst.
I'm sharing my screen here, hopefully.
We've got the whole screen, but here we go. It looks like something's coming. Yeah.
Just switching it over. So
there we go.
So if things are okay, then you should be seeing my first slide. Is that correct?
It looks perfect.
Okay. Well, then I'll start. So to all of you who are taking in this lecture, thank you for joining in. Thank you, Brad, and the Geo-Institute for organizing this live stream, which is part of my deliverables for the Geo-Institute Cross USA Lecture Tour for 24-25. And thanks to my good friend, Jay, who was involved in selecting me and for providing a very kind introduction. So my talk is lessons learned from laboratory full-scale MSE wall testing. And I think that a lot of people that know me already probably already associate me with the work that I'm going to describe here today. You know, mechanically stabilized earth MSE walls, I think all of us would agree, are a mature and proven technology in almost all countries, but this was not always the case. For those who are new to the planet, here are some examples of MSE walls. This is a very famous wrap face wall that was constructed in the late 1980s. It was the highest wrap face wall of its type at that time. And you can see in the cross section that this wall, like other MSE walls, is essentially a gravity structure in which horizontal layers of geosynthetic reinforcement are added to stiffen and strengthen the interior of this gravity mass. So this is a flexible wall face, but also hard-faced walls are constructed. This wall appears to the layperson as a tiered conventional concrete gravity wall, perhaps, or T-wall, but the fill behind the facing panels is reinforced with horizontal layers of a uniaxial geogrid in this example, which is affixed to the concrete panels. So even though these structures are now ubiquitous on the earthworks landscape, there was, at least at the time that the work that I'm going to talk about, where there was evidence that we couldn't accurately predict what the tensile loads and the reinforcement layers rather under operational conditions. And of course, this was an impediment to the development of accurate and efficient design methods for the internal stability design of these systems. So how do we know this? Well, myself and my co-conspirators collected measured loads from instrumented field walls, both steel reinforced type and geosynthetic reinforced type, although I'm going to speak mostly about geosynthetic walls in this presentation. So here is an example of a full-scale field wall. It was actually a test wall that was constructed near Chicago in the late it was in the around 1990. So here you can see a modular block wall, and the right-hand side shows it during construction where a reinforcement layer is in place. You can see some extensometers, and you can see some slope inclinometer casings as well. And from these type of tests, we could gather useful information. So you see a cross section on the left-hand side of the wall. You can see that there's a lot of instrumentation, including strain gauges. And in the middle of the slide, you can see some of the strain distributions that were recorded in this wall during construction and during surcharging. And on the right-hand side, you can see wall deformations, for example. So there was some quality measurements from full-scale walls that was available. Again, that very famous wrap face wall that I spoke about earlier, it was also instrumented. And so during construction and up until the end of construction and surcharging, the strains were recorded in selected reinforcement layers. And from these strains, tensile loads in the reinforcement could be deduced. So from these full-scale walls, the accuracy of load reinforcement models could be tested. And how this was done was that for each instrumented layer in these walls, and all walls, we simply went to the existing design methods at that time and predicted what the maximum load in that reinforcement should be according to theory or the design methods. And this is the simplified ASCE method, if you like. And so here we have in hand the predicted maximum load, and we then compared that to the measured value. So here you have on the horizontal axis is predicted load, and on the vertical axis, the measured load. And if you had a perfect model, these data points would all fall on or close to the one-to-one correspondence line. But this is clearly, at least visually, not the case. And in fact, what we found was that on average, the measured tensile loads were about a third of those predicted using the current ASCE simplified method. In addition to that, not only were the sort of mean predictions of load hugely conservative, but the distribution of loads, as I will show later, was also poorly predicted by this simplified method. We did the same thing for steel reinforced walls. So you can see on the left a steel strip reinforced wall, RICO type wall, and on the right a steel grid or bar mat type. And in these structures, the reinforcement was instrumented with strain gauges. And from those strain gauge readings, again, the tensile loads in the reinforcing elements could be quantitatively deduced. And it was interesting because when we did the same exercise on the left-hand side here of plotting measured loads against predicted loads, there was arguably reasonably good correspondence. And what we figured out was that when these design methods to calculate the design loads in these reinforcements methods, the method was actually empirically adjusted against measured loads, and this improved the accuracy of their load prediction models. But when the simplified method was originally invented, there were no instrumented structures that could give us measured loads so that we could empirically adjust the model to give better predictions. So to better understand how these systems work, we and my colleagues decided what we need to do is to carry out carefully controlled laboratory full-scale wall testing to complement the database of instrumented and monitored field tests. You know, it's very difficult to get a field test instrumented and monitored for obvious reasons. And there's also the issue of control of the construction and the instrumentation, etc., which comes up when you're trying to use a prototype field wall to make these measurements. So this was an incentive to develop an indoors laboratory testing program. And fortunately, we had at RMC, we had the so-called RMC retaining wall test facility. And essentially, this is a pair of very large bookends, you know, reinforced concrete counterfort walls within which we could build these full-scale structures. And here you see one. The front of this photograph that you see here shows a modular block wall. You can see some instrumentation, including these load cells. And reinforcement was extended into the backfill to about almost 6 meters distance. The fill behind this facing was about 70 cubic meters. After construction, we were able to surcharge the structure using an airbag system restrained by these cross beams that you see here. So these walls were 3.6 meters in height and 3.4 meters wide, and we focused our instrumentation over the middle 1 meter wide section of the test facility to get ourselves away from the container sidewalls. Here is a photograph at the beginning of construction where the first lift or two of soil is being placed. And you can see on either side a lubricating, if you like, sidewall system with lubricating oil and vapor barrier to try and create a plane strain test condition to minimize the influence of the test sidewalls. This is the wall when it's about third way up constructed, and you can see the blocks. You can see the reinforcement. These long white things here are extensometers, and there were strain gauges attached as well. Here you can see a walk behind whacker for compacting the soil. And here's a cross section of typical instrumentation for these walls. So you can see that, you know, there were strain gauges, extensometers on the reinforcement. There were settlement gauges, and there were displacement gauges at the front of the wall to measure outward displacements. The contact loads were measured directly. We measured the vertical and horizontal toe loads at the footing and the earth pressures at the bottom of the backfill soil. And in fact, there were over 300 pieces of instrumentation in a typical wall. And some of my friends used to tease me and tell me that I was testing an instrumentation reinforced soil wall. So here is the experimental plan for what I call phase 1 of the testing program, which involved 11 walls. And the start of this program was Control Wall 1, and it was constructed with a segmental facing, 6 layers of reinforcement, a polypropylene geogrid with a strength and stiffness, as you see here. And what we did is we constructed 10 more walls in which one major feature of the control wall was changed and everything else was left the same. So we had different types of facing, a number of reinforcement layers changed, different polymer type with different strength and stiffness. So again, we changed one of these ingredients, if you like, and kept everything else the same. So the idea was that we could then isolate the contribution of the effect of, for example, the facing type, the number of layers, or the polymer type. So here we see a cross section of the control wall, and you can see the shaded area are the modular blocks. The facing was inclined at a batter of 8 degrees. And again, after the wall was constructed, it was surcharged in stages. Here is an example of one of the other walls. Again, it's a modular block facing, but now the facing batter has been increased from 8 degrees to 25 degrees. And the idea is that the difference between wall 1 and wall 8 could be largely ascribed to the effect of the facing batter. Here is a cross section of one of our wrap face walls. You can see the wrapping where the reinforcement continues out and then around and back again to contain the soil at the face. And the shadow that you see in this slide here is the outline of the matching modular block wall, the wall with a harder facing. So we could compare these two walls and ascribe the differences to the presence of the facing type. Here is another example. Here the facing units are incremental concrete panels. I mentioned that we use different reinforcement types, including a polypropylene geogrid, a polyester biaxial grid, and we actually also used a welded wire mesh. And the reason that we use the welded wire mesh, it can be appreciated in this slide. Here you can see the polypropylene geogrid, which was our standard control material. Here's the polyester geogrid with its signature sigmoidal load strain plot. And then we cut the one geogrid type. We removed every second transverse member, and we managed to reduce its strength and its stiffness by half by doing that. And then this material was paired with the welded wire wall test because they both had the same strength, but the welded wire was much stiffer. So this allowed us to isolate the effect of the reinforcement stiffness on reinforcement loads. So here in the top, you see a segment of that previous slide. You can see the stiffer welded wire material compared to the geogrid. Here again, as a reminder, is the cross section of these two walls. And here are the results. The symbols that you see here are the loads that were recorded in the 6 different reinforcement layers in the polypropylene wall. And here the red curve is for the nominally identical wall, but with the stiffer metallic reinforcement. And you can see clearly that the polypropylene material, the extensible geosynthetic reinforcement, generated much lower loads than for the stiffer reinforcement, which is really not unexpected in hindsight, because these stiffer reinforcing elements will attract more load. But importantly, you can see if we use a simplified load model, it predicts that the loads will increase linearly with depth, which is clearly not what's happening for the polypropylene wall. Maybe it's not a bad prediction in practical expectations for the steel. But, this model cannot predict both cases, extensible and non-extensible, to similar levels of accuracy. So it's clear from the examples that I've shown here, just from our lab testing, that it's reinforcement stiffness and not the strength of the reinforcement that is important. Because both of those walls before had the same strength. The reinforcement had the same strength, but they certainly didn't have the same stiffness. Another observation that we were able to make is that the soil and the reinforcement seldom simultaneously failed if you surcharge these walls heavily. And this is in contrast to concepts of limit equilibrium, where reinforced systems are assumed to generate their limiting strength under the same conditions. This was not observed in our tests, and I can show that in the next slides. In the bottom right is the RMC test facility with our control wall in place. And what we did after the construction, we surcharged these walls, and we did that by inflating airbags that were constrained by these horizontal members that you see in this slide. And interestingly, these airbags, they're paper with a plastic bladder. They're actually used as void fillers in railway cars that are only partially filled in order to stop the cargo from shifting around. They're really cheap, and they served our purpose to develop uniform surcharging of the reinforced soil surface. So the plot that you see here traces the construction of the wall based on height and foundation pressure up to the end of construction. And then after construction, we kept surcharging this wall in an organized way until finally there was a failure. And it's interesting, you can see that the surcharge pressure was about 3 times the maximum pressure at the base of the wall at the end of construction. So you can see there's a lot of inherent load capacity in these structures. And what was, of course, very fun for the students is when we had a failure. And here you can see one of the walls, the panels have blown out. They would have gone further if they hadn't been stopped by the instrumentation rack. And when we took the roof and the surcharging system off the top of the model, okay, after we finished with the surcharging and failed the wall, we could see what had happened to the reinforced soil zone. At the front of this picture here, you can see the top of the wall, and you can see a failure scarf which has exited at the top of the wall, and you can also see a crack through the reinforced fill at the surface, which is located at the back of the reinforced soil zone, or if you like, the back of our equivalent gravity structure. And an oblique view that gives perhaps a better impression. Okay, you can see the slump, as it were, and you can see the crack where the internal failure surface has propagated from the toe or heel of the facing up to the surface of the backfill. And what we were able to do, well, first of all, at the end of at the point of incipient failure, we registered the strains in each reinforcement layer, and that's what this sort of histogram thing looks like. And then when we excavated the wall from the top down, which we did in very thin slices, just as if we were archaeologists. And that way we were able to follow the internal failure surface from the top of the backfill down to the bottom of the wall. And what you can see is that this observed failure surface is in reasonable proximity to the peak strains that we observed in the wall. The failure surface is non-linear and perhaps best described by a log spiral surface, and is shallower than the predicted Coulomb or Rankine failure plane that we assume in some of these earlier design methods. So here, during excavation, we would come to a reinforcement layer and we'd take a close look at it, and we would compare its geometry. Okay, the front of the wall is out at the left here, and as you go along, you can see there's the internal failure surface occurred here, and the reinforcement carries on. So the soil has failed, but the extensible polymeric reinforcement was able to continue straining past the point when the soil failed. So that's what I meant by the soil and the reinforcement don't fail together. Other evidence related to failure conditions was that in the database of instrumented field walls, we found that there was no evidence of an internal soil failure surface if the maximum reinforcement strains were less than 3%. So that was an important indicator of the partition between working stress conditions and limit equilibrium or failure conditions. So that meant keep the strains to less than 3%, and there'll be no slumping, no continuous deformations in the wall, etc. And in fact, most walls that we've monitored in the field, the reinforcement strains under operational conditions, the conditions that the wall was designed to resist for its lifetime, are almost always less than 1%. And if you do a tensile test on these extensible reinforcement products in the lab, they'll go out to 10 or 12% strain before they rupture. So this is another indication of the huge redundancy, conservativeness in the design of these walls. Now, these full-scale walls that I was describing to you, I'm sure you can appreciate that they take a fair bit of time and effort to build. And just for your entertainment, typically during the decade that I was doing these tests, I would have a master's student who would be responsible for organizing the construction and the instrumentation and the monitoring of these walls. Now, these were special master's students because they were all serving military officers, so they were perfectly fit to do this type of research because they were trained to be organized and also not to talk back to their supervisor. However, it took a lot of time, so we carried out another parallel investigation in which we built similar models, but at 1/6 scale. So here you can see such a structure. Here the walls are only 1.2 meters in height, but had the same similar instrumentation with connection, load cells, airbag system, and lots of instrumentation. So here you see a cross section. But the advantage of these reduced scale tests, where of course we could build them at a higher rate of production, And we could also test other things that were not convenient at full scale, including using rubber mats and foam pads, etc., to simulate more compliant foundations, and thereby see what influence would these more compliant foundations compared to a hard concrete base foundation have on the performance of the reinforced fill and its deformations. And another advantage of these tests was that that box that I showed you had transparent sides. So we were able to use DIC monitoring to track the deformations in the reinforced fill. And what you can see at the end of surcharging of this wall, you can see the development of what we call contiguous failure surfaces. So this is right at the point where the wall failed. And gee golly, and maybe it was just good luck, you can see that the maximum strain is about 3%. So maybe that was fortuitous, but I'll take the win. Oops, sorry. So another observation is that we found that the distribution of maximum loads in the reinforcement layers was typically not increasingly linear or linear with depth. It was usually bilinear. And we demonstrated this by taking all of the measured loads that we had recorded in full-scale field walls and plotting them on this normalized plot, where the horizontal axis is the maximum load in a reinforcement layer divided by the maximum load from all instrumented layers. And on the vertical axis, just normalized height of the wall. So the light gray symbols that you see here are the predicted values, assuming sort of the current limit equilibrium method of calculating loads in reinforcement layers. And you can see they fall more or less linearly with depth. The measured results, which are the open circles and the filled circles, are actual data. And if you want to capture that data, then you're better off with a bilinear distribution, not this linear distribution. Another important and practical observation was that we found that the maximum loads in the reinforcement are more likely to occur at near the connections than at locations predicted by an assumed internal failure surface using simplified methods. I showed you that alignment between a Coulomb surface and the internal peak strains. But under operational conditions, this is not the case. And it's most easily demonstrated by looking at the results from our wall tests, including this incremental concrete faced wall. So this is relatively rigid vertical structure. That is the facing. And if we focus our attention on the connections or the strains in the vicinity of the connections, we get plots like this. So each one of these subplots is one of the layers in this lab wall, and the symbols are the actual measurements. And if you focus on the symbols, you can see what I mean. They're generally the highest ones are close to the back of the wall. As a sidebar, you can see a bunch of continuous curves here, and these are predictions based on different soil models. And these physical results are seen to be in reasonable alignment with the predictions, which demonstrated that our numerical model was doing a reasonable job at predicting the performance of these actual physical walls. So the question is, what is going on? Well, what is going on is that when this wall is being constructed, the soil is being placed and compacted, it moves downward relative to the facing, which is vertically rigid. There may be some additional vertical settlement of the fill as the wall moves out slightly. And what that does is it puts what I like to call parasitic loads on the connections, which are not predictable using force-based limit equilibrium methods of analysis. And so we saw this in our physical models under carefully controlled conditions. And we also saw this in full-scale field walls. This is the what we call the SR18 wall, which is you can see the cross section here. These are production walls built near Seattle and Washington State. They were instrumented, as you can see in the cross section. You can see the technician attaching extensometers, etc. And if we look at this layer 4 at the top, you can see, yes, the strains are greatest behind the facing, because again, the soil is settling with respect to this relatively rigid facing system. Other important practical observations is that that the reinforcement creep is very low. The creep rate is very low, and the expectation that the reinforcement will creep to rupture during the lifetime of the structure is just not supported by observation. And in our tests, the walls were only left for short periods of time. We saw that the creep strains were not increasing with time, but a better example, again, was that SR18 wall that I just showed you, where we were able to monitor this wall for 2.5 years almost after it was constructed. And when you plot the strains in the reinforcement with the log of time, there's no way that these strains will increase dramatically under typical design lifetimes. So creep to rupture is not a problem for these structures, if they're built and constructed and designed correctly. I talked about the experimental design where we wanted to compare the effect of a wrap face wall to a rigid face wall to isolate the influence of the facing. So here you can see these two walls side by side. Here's on the right hand side is the control wall. The left hand side is the wrap face wall. And here I am, much thinner decades ago. And so here we focus in on approximately the same layer elevation in these two walls. So the wrap face on the left, and this is showing and the block faced wall on the right. And if we look at this curve here at the this plot bottom left, you can see the strains in the reinforcement are quite low compared to the strains at the same nominal locations for the wrap face. And this is because the hard facing helps to carry the loads that are being generated by the fill, whereas the wrap face is too flexible for that. And this difference in performance persists when we surcharge the walls, and that's shown on this plot to the right. Now, when I was doing these full-scale walls, I was pretty proud of myself, thinking that I had the market cornered. But my good friend, Professor Yoshimiyata, at my sister Armed Forces College in Japan, the National Defense Academy, took me over to a research institute in Japan, the Public Works Research Institute, where they had some really big full-scale test walls, as you can see here. And what I found out was that in Japan, if you are the owner or you're selling or distributing a reinforced wall, proprietary system, you have to prove to the government that these walls will work. And so they make you build truly full-scale walls, 6 meters high, instrument them, and test them. And only then do you get sort of call a certificate of approval that you can sell these things. And so over a period of 20 years, this data has accumulated. And this data was given to Dr. Miata and myself to increase the database of wall performance. And this data proved really quite useful. Here you can see some slides of some of these walls that they built. Here's an incremental concrete panel wall, top left. Here's a wall that they built with a plywood panel face, because they too recognize that the stiffness and the flexibility of the facing is going to have an effect on the loads and the reinforcement. And here's another one where they simply used sandbags as the facing. So Dr. Miata and I got a lot of mileage out of those walls. And not only were they building, the Japanese building full-scale indoor test walls, they're also building full-scale walls in the field. And here is an example of a pair of walls that were built not very long ago in Nagasaki, Japan. And you can see the cross-section of the wall, and you can see the reinforcement layers and the surcharging system. But the neat thing was what they did is they built a pair of these walls side by side. And the only difference was on one side they used steel strips, and on the other side they used PET strap. And you can see the two reinforcement materials that I'm speaking about here. And this, a comparison of those two walls allowed the influence of the stiffness of the reinforcement to be isolated. This other picture that you see here is a test on a sacrificial piece of PET strap reinforcement to test the connection and also the interaction or stress transfer between these PET strap reinforcements and the fill. So after spending a day on site here, Yoshi and I would get in our best kimonos and we'd go to a fancy restaurant near the site and quench our thirst. So practical consequences of these test programs were reinforcement loads under operational conditions are much less than loads predicted using current limit equilibrium-based methods. There's excessive amount of reinforcement, 2 to 3 times. The reinforcement is not located in an optimum direction. And something that I can't touch on here, because the loads are so high, it's impossible to calibrate reliability-based LRFD design limit states. How to fix? Well, the current simplified method is shown by this equation at the top here. And so what we did, I guess in a way, we borrowed from the structures guys, and we took this equation at the top, and we just we modified it by introducing correction factors that you can see in this lower equation. These theta terms are all empirical, non-dimensional correction factors. And we called this the stiffness method because a major ingredient in the calculation of the maximum load was the stiffness of the reinforcement. So then when we went back to our database of both geosynthetic and steel reinforced walls, which you can see on the left-hand side, and we corrected our predictions using this stiffness method, you can see on the right-hand side, at least visually, the predictions are much better. Now, this is a pretty scary looking equation, but in practice, for most walls, some of these terms disappear. At least their value becomes 1 or 0, and the equation becomes much simpler and arguably not much more complicated than the so-called current, which is now past ASCE to a simplified method. In fact, this stiffness method is now specified for internal stability design of geosynthetic mechanically stabilized earth walls in ASCE 2020. And it's an accepted method in the equivalent Canadian Highway Bridge Design Code, although in the Canadian code we use it for both extensible and inextensible. And again, the signature feature of this approach is that it uses the stiffness of the reinforcement as a key parameter to calculate loads under operational conditions. And this is a paradigm shift from the simplified method, which was based on the soil strength, not its stiffness. Another bonus, and I'm going to say a few words about this, is that if you're in the business of numerical modeling, and my last webinar focused on numerical modeling, these full-scale, carefully instrumented and monitored MSE wall structures at RMC are perfect to test against numerical models, perhaps using FLAC or finite element methods. And this allows you to test the veracity of your numerical code. And here's a pretty picture which has been developed from one of our simulations. It allows you to see the distribution of strains, the magnitude of the strains, and the like. And here is a slide which gives an example. So here's this wrap face wall that I spoke about earlier. The symbols are the loads in the reinforcement layers, of which there are 6. The solid symbols that you see here are the measured results. And then the other curves and symbols that you see there are predictions based on numerical modeling and analytical models. But you can see that that the numerical model's not doing a bad job. They're more or less in the same vicinity of the measured results. So that was a demonstration of the veracity of our models using the results of just one wall model in our suite of tests. So I'm going to stop there, but I'm going to finish by just giving a shout out, first of all, to my long-term friend and collaborator, Tony Allen. He was until recently the state geotechnical engineer in Washington State, and he was until recently the chair of the technical committee on foundations and walls in ASCE. And he's the guy that put me onto this problem. He said, Richard, we need a new design method. What can we do? And I said, well, I have this test facility. And he helped to arrange funding through a pooled fund of something like 12 DOTs in the States. And I was able to scrape up money from Canadian sources and various companies. And that's how this work was financed. But the true slogging was by a large number of graduate students. Their names are here. The majority of them, as I mentioned before, were serving military officers, but there were a few civilians in this bunch. And to them, I want to express my gratitude. If you're interested in this work, you can just go to my webpage. It's easy to find. You can just Googlate me, and you can find these papers. If you can't get the papers, I'm more than happy to send them to you. That concludes my talk. I thank you all for your attention. Hopefully we have a few minutes for questions.
Very good. Thank you, Richard. Excellent presentation. Just real quick, could you just give us the basic definition of stiffness versus tensile strength?
it's best realized in, let's see, if I go back to an earlier slide. We're flipping back. Let's be patient. Oops, I don't want to see that too often. I'm sorry, I should probably just... I'm just trying to slow you down, Jay.
Okay.
Here we are. So what I'm going to show you is the slide that I showed you about the different there. Let's keep going. Here we are.
There you go.
So tensile strength represents the load and the reinforcement that you record at the end of the test at the point that the reinforcement ruptures. Okay, and different products have different tensile strength. Stiffness is, if you like, simply stated, is the slope of this line at very low strains. And it's this initial slope which is important to characterize the behavior of these materials under what I call operational conditions.
Very nice. Okay, so operational conditions. So that's not considering any reduction factors for, let's say, installation damage, durability, or creep, correct?
No, we in design, we use a strength which is lower than the ultimate strength by dividing in those factors that you just talked about. But the basic calculation is based on a reduction of the ultimate strength, which bears no resemblance to the stiffness of the material under operational conditions.
Okay, the FHWA wall, one of your first slides, showed considerable strain versus time. Would that be a creep response that we're seeing there?
What happened with that wall was that after the wall was constructed, they purposely wanted to overload the reinforcement so that they could see what was, if you like, the true margin of safety. So what you saw on that slide here, I think this is what you're, okay. Yep. So what you can see is there's fairly high strains, if you like, but these were developed after surcharging. So the lowest values from memory, just to say this +1, yeah, here's surcharge 0, okay, but the highest strains were recorded after the wall had been surcharged. But even then, the strains were not hugely excessive, because remember what I said is, we typically get 1% under operational conditions, and these reinforcement materials can go to much higher strains. But they did this because they designed this wall using the simplified method, and they designed it so that at end of construction, the factor of safety against overstressing the reinforcement was 1. And thereby, by putting a surcharge on top of this wall after end of construction, supposedly the wall would fail according to the design methods of that time. And the wall said, no problem. So this was, again, proof positive that there was a huge amount of redundancy and extra capacity in these walls using the methods at that time.
Very nice. Okay. I'm going to go to the audience. Patrick Mans asks, were the results obtained from the settlement gauges used to compare the wall behavior founded on various soil types?
The answer is no. The only way that we could examine the effect of the foundation type was to use those reduced scale models. However, we were able to use our validated, if you like, numerical models of our walls that were constructed and simulated with that rigid base, and in the numerical models soften up the foundation. And that way we were able to study or observe what effect that compressible foundation would have on the distribution of loads and strains. And I think in my last webinar, I showed the results of that type of numerical simulation. And yes, the effect of the compressibility of the foundation influenced the loads in the reinforcement. But we found that it was still the stiffness of the reinforcement that had more of effect than the compressibility of the supporting foundation.
Before we go to the next one, Richard, do you want to stop sharing? And Jay, you got to turn your camera on. Let the people see you.
Okay, I will stop sharing.
This way we'll go split screen. There we go.
Okay.
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 Go ahead, Richard.
I think what I'll do is I'll end my slideshow, and that way I'll just flip through my slides if we have to. Next time it's faster.
Okay, while you're doing that, I'll offer up a question from Jason Ansley. For your full-scale tests, which I'm very glad that I was never your grad student.
I was a tyrant.
I'm not built for that. What materials were used as backfill in the reinforced zone, and did you do any comparison with differing reinforced zone backfill material?
That's an excellent question. In that phase one that I was talking about, we wanted to simplify these structures as much as possible in order that we could investigate the major principles and behavior, etc. If you start introducing more variability in those parameters, then you may not have as useful a test matrix, if you like. So what we did is purposely we used a high quality sand fill, and we used that because it was easy to quantify its parameters. We did very careful triaxial plane strain testing, etc., in order that we knew exactly what the properties of that material were, and we could use those results to find parameters for constitutive soil models of varying complexity. However, having said that, there's a phase two in which we used a much more silty material. I think it was about 50% silt in it, in order to isolate the effect of the backfill soil. And I'm embarrassed to say that I haven't written those up yet. So we sort of ran out of time, I guess. But again, using those numerical models that I spoke about, once they've been calibrated, it was easy then just to change the soil model to simulate what we would believe to be, for example, a lower quality fill material.
Michael Rivas asks, was the maximum load still at the facing connection for metallic reinforcement, or did the metallic reinforcement distribute load more uniformly?
Actually, no, it was still largest at the facing, but the thing is, the extensible reinforcement materials are better able to redistribute load than the metallic materials in our experience. And we've actually seen that in full-scale field walls, where we have some hill flicker walls. These are, steel grid type walls, and the connection is pretty rigid. And we actually found that the loads and parallel longitudinal members of the steel was much more variable than what we would see in comparable walls with extensible polymeric reinforcement.
Okay. Just for everyone, if you have any questions, go ahead and just type them into the chat, and I'll repeat them to Richard. Richard, Sadupta would like to know more about the airbag you use for the surcharging. Could you perhaps elaborate a little bit on that?
Well, like I said before, they're actually giant paper bags, like, fiber reinforced paper bags with a polyethylene bladder. They're about 8 feet by 4 feet or something like this. And you blow them up and they make a sausage. And they're used in as void fillers in railway cars, so that when the railway car is jerking around, these void fillers buffer them and prevent them from crashing into each other. So we were buying these things by the pallet load, and then we had an air pressure, a compressor, and we would just blow them up, and they were just fit for purpose, and they didn't cost very much, because a lot of people before us were buying really expensive, Kevlar reinforced bags that cost millions of bucks. Mm-hmm. And we would just throw these in, and occasionally they would pop, right, and they would make a big noise and scare students, but we would put them in layers as well. So if one bag popped, the other bags that were inflated could still maintain the surcharge pressure.
Okay. Right. Understanding that stiffness is controlling the design, could you perhaps comment on tall walls where the simplified method would be calling for very high tensile strength geogrid reinforcement? Is there a fundamental problem with the design using simplified method at that point?
Well, there's one of the talks that I have given as part of this lecture series was on the issue of, how and why did we go from the simplified method to the stiffness method? And there are situations in which both methods will give you a similar load. And what we found is that if you do have very high walls, there is practical agreement at the top of the wall using the two methods. But at the bottom, and over, say, the bottom half or third of the wall, you'll find that the simplified method over predicts the loads in the reinforcement by large margins, not unsimilar to the ones that I just showed you.
Right. Yeah. Okay. Well, thank you, Richard. That's Brad. I think I'm going to turn it back over to you. So thank you, Richard, for sticking around to it. Back to Brad.
Okay.
That happened fast. I wasn't ready. Thanks, everybody, for watching today, and especially for those viewers who contributed questions. That's really where it adds the value to doing these as live streams. We really do appreciate it. Richard, fantastic lecture. Jay, thanks for your moderating skills as always. We are thrilled to have you. Every year when it comes to Jay's turn, I know it's going to be good. And since you and Richard were such buds, I knew it would be good. Now, I do want to take issue with one thing, Richard. When you answered that question about the airbags, you said that when the Kevlar ones popped, they scared the students. What you are implying by that is that you, as the astute professor, were not scared when this happened. Is that true?
I was always, looking through a window at some distance.
Ah. So you're not in the line of fire, as it were.
No, but
actually, he was in his kimono drinking, and
That's
they were
right.
in the lab.
The truth of it is that you really couldn't predict when they were going to go, because these surcharge loadings were left on for a few days.
Oh, okay.
And so sometimes there was an explosion at night, but there was a couple of occasions where there was an explosion during. But the kids love it, they love to break things.
It does actually lead me to a question, because when these things are used in the rail industry, they're obviously subject to some pressure, but probably nowhere near what you were putting on it. What do these things max out at?
Well, this is it. We were loading these bags up to 3 times their rated pressure.
Okay.
So there was always a good chance that things would go badly. So yeah.
I love that. That's good. I'm so happy I got a chance to ask a question today. Usually that doesn't happen, so I'm thrilled by that. So for all of our viewers, again, if you liked what you saw today, and you must have because you're here at the end, of course, click like, subscribe, and get notifications. And yes, we'll let you know every time we post something to the YouTube channel. Our next live stream is in just 7 days, and it is our first preview for the Geo Extreme Conference, which is coming up this November in Long Beach, California. Our preview presentation is going to be by Taki and Pavlo Crisaveragas. Yes, they are related, on the 2019 California wildfires. You can register for that on our Eventbrite channel page, as well as all the other upcoming events we have during this summer of live and beyond. Richard's third live stream in this series will be on September 11th, one of the closer outers for the summer of live for this year. Maybe it'll be getting a little cooler by then, probably not where I live, but maybe in some parts of this continent by that point. Again, make your contribution to student programs, get your Ralph Peck bobblehead or one of the other amazing giveaways. We hope to see you at another live stream soon. Our producer today was Aurora Flieger, and we will see everybody very soon with another Geo-Institute event.